Welcome back to the sixth part of my simple constant current load. We're not quite where I left off last time. Yeah, I removed most of the cables and I'm back to battery power for the unit. Yep. And we will talk today about reverse voltage protection. Not for, the battery supply. There we have one, and it was already very useful because in the last part, card link, I actually managed to connect the power supply the wrong way around when we are testing out the low battery indicator. So I also will need, I will need a reverse voltage protection for my binding posts. I'm totally capable of connecting them the wrong way around, obviously. And I'm still going through the, 5 phases of grief regarding the lackluster performance of my heatsink. At first I was in denial about what I've measured, so I actually repeated all the measurements, but I was within 0.05 Kelvin per watts within the first results, so it was not performing as expected. Then I became angry and I cursed the vendors of the thermal pads and the heatsink. What they write in the data sheets must be total BS. And finally I started bargaining. I mean, do I really need 10% security margin here? I mean, my measurements obviously are quite accurate. And do I really need 40 degrees maximum ambient temperature? I mean, 35 should be okay. And I'm currently still in the depression phase about all this, so we do the reverse voltage protection first. Warning! Again, like in the last video, I won't show you the finished product. For that, use the time index in the description. Instead, I will go with you through all the loops and cul-de-sacs I went through in developing that reverse voltage protection. So again, you are in for quite a ride. So, reverse voltage protection, and that would be that blue box here. And no, I haven't updated the rest of the circuit diagram yet. Well, let's have a look at the details. Just for your orientation, 0 volts to 33 volts buggers off to the positive binding post, and this line buggers off to the negative binding post. And in here we come from the current regulation, where the current comes out. The op-amp works as a comparator, like in our low battery indicator. And if I haven't put a card and link in, I will do it now. So comparator, we have two nearly identical voltage dividers here, quite extreme voltage dividers. So 51k to ground in each case, and 10 meg, one side to the positive binding post, so 0 to 33 volts, and 10 meg to the negative binding post. So basically we get the input voltage to the constant current load scaled down to the positive and negative input of the op-amp. And scaled down, I mean for 100 millivolts here, I get half a millivolt here, always compared to ground. So if I have some positive voltage here, let's say positive 100 millivolts or positive 200 millivolts, I have positive 2 millivolts here at the input, and if this is really 0 volts compared to ground, I have here, of course, 0 volts. And how that works is self-explanatory. As long as the positive input is positive, more positive than the negative input, my output will go to my positive battery rail and therefore switch on that MOSFET, which has, I think, RDS on 5 milliohms. So really, really low. And as soon as the negative voltage becomes greater than the positive voltage, so I basically, what I like to do, switch around the input leads, put them in the wrong way. This output of the op-amp will go to ground, basically shutting off the MOSFET, and then, no current can flow through here. The body diode, we have drain down here, source up here, is in the right direction to block a current flow in the wrong direction. So let's wire that up first without that resistor here. We talk about that in a minute maybe. Just the voltage divider, the op-amp, and the LED. We are buggering here off to the cathode of the red LED with a 2.2K resistor. I wired everything up. We will have a close-up look in a second, but you can already see weird things. So I'm measuring with the oscilloscope the output of the op-amp, and it's about a nice oscillation, DC content 6 volts. And you know, something else, can you see the red LED there? Oh, probably not. Maybe you can see it flickering, but as soon as I put my fingers just here in the vicinity of the binding post. And that's with absolutely no input connected. So, what's going on here? Sorry for the probe cable. It's in the way. So we just have these two voltage dividers, and this is, to the ground and to the positive binding post where nothing is connected at the moment. And this is to the ground and to the negative binding post where also nothing is connected at the moment. So basically both inputs are connected through, relatively, for these op-amps, extremely small resistance to ground. And the op-amp is not in a stable state because, no feedback. It works as a comparator and it gets two identical input voltages. That is 0 volts, ground. So, quite unstable. And that's why this little offset resistor is here to give, especially in that condition when absolutely nothing is connected, a little bias to the positive input, driving the output stable to high, hopefully. So I will add that thing now. So there's really not much to see on the board. Besides that, I have forgotten the decoupling capacitor for the op-amp. But okay. So these are my two inputs, positive and negative, and these two resistors and these two resistors are my voltage dividers. That buggers off from the op-amp output to the LED cathode, and yeah, that's newly added to the positive input, the 250 mega ohm resistor, yeah, which is powered from my 2.5 volt rail. Let's have a look how that works. And that doesn't work quite sufficient. See, when I just put my hands here, yeah, I can make it swing. Yeah, could be the missing decoupling capacitor on the op-amp power supply, or 250 meg might be a smidgen too much. Yeah, too little voltage offset for the positive input. Let's correct that. Was not the decoupling capacitor, and I'm down with that bias resistor now to 50 meg. I can still, yeah, move my hand here and nothing bad will happen. I have to actually touch the terminal, and the waveform you see here is exactly 50 Hertz. So what's happening, I'm acting as an antenna, catching our country's 50 Hertz mains AC and coupling it into the circuit, which is okay. I mean, this is a reverse voltage protection. It yeah, should be sensitive, but maybe I go down to, well, let's see, 25 mega ohms. I decided to stay with 50 mega ohms. I tried 25 meg and it didn't really improve anything. And these 50 mega ohms now give me an offset here of 2.55 millivolts with nothing connected to the positive binding post. Yeah, in comparison, 100 meg gave me 1.27 and 250 meg 0.51 millivolts, which is, yeah, a little bit low if you consider the offset voltages of that op-amp here. Anyway, to get that point down to 0 volts, I have to apply here only minus 250 millivolts. Yeah, the whole thing is an resistor adder unit, if you look at it. 2.5 volts here through 50 meg, and whatever comes in here through 1 meg. So 5 to 1 mixing. And yeah, 2.5 volt, 250 millivolts. I think I can live with that. Let's wire up the MOSFET and do some more measurements. Let's forget about the oscilloscope for the moment. I have 1 amp flowing through the thing here at 20 volts. And this is displaying the voltage drop across the MOSFET, which is almost non-measurable. Yeah, it should be, yeah, around 5 millivolts, but that's so low that, yeah, if I just touch here the leads, yeah, so yeah, in normal operation that seems to work just fine. The question is, what happens if I now really apply reverse voltage? Still not applying reverse voltage, but I, yeah, beefed up the measurement stuff a little bit. Yeah, it gets crowded. Anyway, this is now measuring the current that goes through the thing in milliamps. This is measuring the voltage across the terminals, and you see at the moment I have 10 volts across the terminals. And I have, yeah, hidden back here, can you see that? Probably not. Oh yeah, you can see it here. A 1K resistor to make the testing not too destructive. Yeah, and all wired up with the correct polarity and of course with 1K here. As soon as I turn up the current, just one turn, the voltage drops down and I have my aboutish 10 milliamps going through the whole thing. And now comes the interesting part. So I will turn the voltage down. And the blue line is still displaying the voltage across the gate of our MOSFET, which goes relatively quickly to 0 if I switch off. So I'm at 0 here. I'm reversing the polarity. And I go to millivolts here. So 0.55 millivolts across the terminals. I turn that also down. Now I have -7 millivolts across the terminals. And my red LED, hope it's not blocked. No, you can see it. Oh, yeah, barely. Sorry. My red LED is not on. And now we tweak up. Okay, 30 millivolts. So I suspect at about 100 millivolts or so, or a few hundred millivolts, the reverse voltage protection should kick in. 200 millivolts. Still not getting nervous. Okay. Now I'm getting nervous. Okay, now. No. Not working. Why not working? I mean, sorry, police is coming for me. Why not working? Well, it was actually working, but only when you put a volt negative across the terminals, and the culprit was my 50 meg offset resistor. And now if I turn the voltage up, the blue line is the output of the op amp to only, you see it already going down, but basically at 250 millivolts negative input voltage, the thing totally clamps shut, which is what I wanted. The problem now is if I'm in the correct polarity, 50 hertz, we have again the problem with the LED slightly being on. Can you see that? Yeah, you can see it glow. And the LED only shuts completely off if I apply a positive input voltage of at least 100 millivolts. You could live with that, but frankly, I don't want to. Yeah, let me think about that one. Just as a side note, with my 250 mech back in as bias resistor, the LED is off, and I'm still, yeah, practically off at minus 350 millivolts. Yeah, no current flowing whatsoever. Would be one solution. But I want to try something else. And yeah, as soon as I go back to nearly a minus 7 millivolts, LED is off. Now we're getting somewhere. So no input, LED is off, and I increase the negative voltage, minus 23 millivolts, 150, 200 millivolts, nothing happens, and then very sharply it goes down. So it falls down at, yeah, 270, 275 millivolts, and very quickly. So let's try it with the polarity, or first what happens if I have nothing connected. LED stays off. Wonderful. And I can even touch, can I? The metal of the terminals, and the LED stays off. And if I have the polarity the right way around, yep, everything is just perfect. Okay, now I'm out of range. Sorry. So, what exactly did I do? I completely ditched here that positive offset resistor, and instead I'm using now a 250 mega ohm positive feedback resistor, basically turning the whole thing into a Schmitt-trigger. That first prevents all that 50 Hertz stuff and flickering of the LED, and also provides a deeper switching characteristic when a negative voltage is applied. So yeah, that looks good, and it's time to remove the 1K protection resistor from the power source and test some more. So the big moment, I'm directly plugged into the power supply without that little 1K resistor, and if I turn the voltage up in reverse polarity, no current flows. Yeah, look at the ammeter, and at 200, yeah, 275, we already saw that. Reverse polarity protection comes on, and I can basically increase the voltage. Yeah, there's a little leakage current in the sub-milliamp area, but yeah, 2 milliamps, okay. I won't destroy anything with that. And yeah, I can also turn up here. No current is flowing. Wonderful. And if I put it the right way around, okay, here in that 200 milliamp range, so I should try not to kill it. Everything just works. Oh, already over. Everything works hunky-dory. Yeah. And yeah, I'm in the millivolt range, so it doesn't display anymore. Next, I want to see how fast that inverse voltage protection works. And yeah, I have specific settings here. So if I try the same stunt again, reverse the polarity. Ooh. Sorry, reverse the polarity again. Yeah. Wonderful. Just a single shot of the gate voltage of the MOSFET when negative voltage is applied to get an idea how fast the whole thing is working. And 1 unit is 1 millisecond. So you see within 4 milliseconds everything is over. The thing is off. Which is quite okay. Could be faster if you would use a MOSFET driver, but then it's a simple constant current load. And 4 milliseconds reverse voltage, yeah, stuff should survive. And here is the final circuit, nicely drawn, and I wanted to make an additional point about the input voltages and the special op-amp here I chose, the TLC27L2. So let's suppose, yeah, you remember this is buggering off to the positive binding post and this is buggering off to the negative binding post, and yeah, apply an external voltage, let's say plus here, minus here. Then of course through the voltage dividers and ground a current is flowing. So I have a voltage drop across this resistor and I have a voltage drop, yeah, relative to ground over this resistor, and that means this input here is negative compared to ground, and this one is of course positive. And if you remember, yeah, only have the small picture here, sorry, the power supply diagram. The negative rail of my op-amp is ground and the positive is battery. So if I would, sorry, draw that in here, this is ground and this buggers off to my 6 to 9 volt battery rail, meaning my input voltage here is below the negative rail of the op-amp and it's still working. And yeah, to understand that we have to have a look at the data sheet of the op-amp I choose. So these are LIN CMOS, so CMOS technology, precision dual operational amplifiers. And my primary reason was I stumbled upon them. I was looking for some op-amps with really low offset voltages, because inside the current regulation with the really small voltage drops, yeah, when you just adjust for a few milliamps of current in the current regulation, I didn't want it to deal with offset voltage. Okay, that was my primary reason, and I searched for affordable, yeah, this thing costs $1.20, affordable op-amps with low offset voltage. And yeah, that thing also has a low, which is a must, supply voltage, yeah, 3 volts to 16 volts, because, yeah, battery-powered device, yeah, a single supply operation is a buzzword. You can basically, yeah, operate any operational amplifier with a single supply somehow. And this one, and this is a really, really nice feature. I mean, output voltage range includes negative rail. Wow. So even if it's not officially a rail-to-rail op-amp, the output can really go down to ground, to 0 volt. And of course, we talked about that before, the high input impedance of 10 to the power of 12 ohms, typical. So not mega ohms, not giga ohms, I don't know what comes after giga. You tell me. Something else here. Nah, something. Yeah. Oh, I forgot the most important thing. Common mode input extends below the negative rail, and yeah, this is a fantastic feature. Yeah, I used it obviously, and yeah, you have to search a while until you find an op-amp that can do that. And here in the absolute maximum ratings, you have the input voltage range, any input, positive or negative input, minus 0.3 volts to VDD, so your supply voltage. And yeah, that's the reason, you remember that, I dimensioned these voltage dividers. So at plus minus 60 volts in, I only have plus minus 0.3 volts maximum here. Yeah, and finally the input offset voltage highlight. Yeah, for the type I choose, there is one a little bit more expensive, a few dollars available, but mine has a typical offset voltage of 204 microvolts, not millivolts, microvolts. And you, yeah, worst case, okay, 2000 or full range if you really heat it up, 3000 microvolts, so 2 or 3 millivolts, but typically 204 microvolts. And you can buy one with 170 microvolts, or absolutely worst case 1.5 microvolt offset voltage. Again, yeah, the common mode input voltage range, typical down to minus 3 volts, and low level output voltage goes down to 0 volts, or worst case 50 millivolts. So yeah, very, very nice op-amps in that respect. And that's it. Reverse voltage protection successfully implemented. Yeah, we went through some loops, and at the end we changed the circuit quite a bit, but now we have a really nice working solution that does everything I wanted. Don't know about you. So next stop, finally, and yeah, my grieving process, it's finished now. I'm accepted that my heatsink doesn't dissipate 25 watts. So yeah, next stop will be the power/current limitation here, dependent on the voltage drop. Till then, bye.